Okay, can you please confirm that you can see the first slide?
We can see and we can hear you.
Perfect, thank you. The second part of the webinar will be about power monitoring of HPC hardware. I'm not sure whether it was me or someone else, but please mute yourself if possible.
Done, muted.
Thank you. Okay, so it will be about power monitoring, and I will tell you in next slides why I'm speaking about power monitoring, not about energy measurement, because it's more precise. So first of all, I'm not sure whether you can see an equation, because in my preview it's not visible. There is just a shading line, but there is that energy is evaluated as power multiplied by time, where the power is the energy, not energy, but the electricity consumed at that moment, at the specific moment. So not in time. If we want to evaluate consumption in time, then we have the energy. So power is in watts. However, energy is in joules. It is the basic unit. So consumption of 1 watt for 1 second is 1 joule. If the time range is 1 hour, then we may speak about watt-hour unit, which is, let's say, more common, because in joules the unit would be too high. No, not the unit, but the values would be very high. So obviously, the energy or power consumption during the time is not stable. So it's not a square where we just multiply a single power information by time. But since it grows up and down, we must take samples. So we take samples in time and then interpolate the value from the power samples. We get at the end energy consumption of some application in our case, or better say of the hardware when executing the application. So here I have an image of power samples in a line chart where some application is running. So you can see at the end some probably iterative solvers. So there are loops, and power consumption is different into previous parts of the application. So as I said, there are samples, and we are interpolating the overall energy consumption. There are various power monitoring solutions, and it depends on what level of the system we measure. So we may obviously measure the whole building, because the HPC center must pay bills for the whole electricity they consume, but we can go to these are usual levels at which we monitor power consumption, but obviously there could be some specific, or potentially some of them may be missing, but usually data whole system of each rack. And in our case, when measuring energy consumption of an application, we should really focus on a node power consumption, because if the application, we are allocating for the application specific number of nodes, so that's the power consumption we may influence. So that's the power consumption that goes behind our application. And then we have power monitoring on components on node, typically CPU, GPU, FPGA, or any other kind of accelerator, memories, and interconnect. So these are kind of the usual ones. On Node power monitoring, there are kind of a list of available ones. This actually this table is kind of outdated because there are some more. But what I want to present in here that there are various purposes for what reason why the power monitoring has been established and why someone created such an interface. And due to that purpose, it has its specific parameters. So typically, sampling rate, how often it samples, and whether it really needs high frequency sampling that is good for precise energy measurement and potentially for understanding of a short part of your application, how it works, because the power consumption may give you insight into your application behavior. And so that's the sampling rate. Important part is what power domains it has, what part of the hardware it monitors, and then in-band and out of band interface, which is how you can get the information from the power sample. No, sorry, not from power sample, but from the power monitoring system. So we have in-band and out-of-band. In case of the in-band, we typically mean some performance counters that you can read, for example, by the perf, or out-of-band, where the information is not directly, or the power monitoring system itself does not provide it to user space, but there must be some other way how to expose to user space the information, where it the monitoring of itself, it's going without influencing the CPU. That's the major information, a major parameter of that. While exposing the information to the CPU has quite high overhead in compared to in-band solutions when reading the information from the typically from the CPU, like reading the performance counter. Example of the out-of-band solution is HDIMM, which is hardware that has been accommodated on directly on board on computing boards, blades, developed by Bull with cooperation with TU Dresden, but in a few years, more than a few years ago, and Bull does not exist anymore. Atos seems that almost too. So this is a solution that is not available in latest evidence systems anymore. However, it's still available in some older systems. For example, IT4I has one of these Cascade Lake based, where there's really a hardware solution that samples 1,000 power samples of the whole blade per second, and it stores in its internal memory. And then using kernel module, it expose then the information from the internal memory to the application, provides you all the power samples it stores, or just the aggregated information, how much energy it has consumed in a specific time period. Or then we can go to in-band solution, which is most well known, is the interface that is available on Intel CPUs from Sandy Bridge, if I'm right. So it's Intel RAPL running average power limit. So if you can see from name of that, it is power limit interface. So it has not been really designed to measure overall energy consumption. It is kind of side effect, but it's designed to provide you power capping solution for your CPU. So yeah, there are various power domains specific for whether you have a server CPU or mobile CPU. So on server CPUs, we have the package and DRAM. On the latest CPUs, there's supposed to be also the platform power domain. Package is just you can see in the image on the right side. So the package is the yellow box only. Yeah, so it's providing power consumption of your CPU, but not the whole CPU. It's important to know because when you buy a CPU that has a TDP of 100 watts, or rather say 1000 watts almost nowadays, the power limit is evaluated for the package domain, while the DRAM domain is outside of that. So actually the CPU consume even more than the TDP, but the TDP is specified for that one specific power domain, which is controlled. DRAM has its own power limit, but from what I know, it is on all at least server CPUs, it's turned off. But user, if has access to that, it's possible to play with that and turn the power capping on this power domain also. So the CPU changes core frequency based on the information in the evaluated or time window, where so it samples the power, and it has specified really a time window, running average power limit. And if the average power consumption exceeds during the specified time window, then the CPU is being can someone mute, please? So the CPU or the RAPL downscales the core frequency of the CPU, well, both core and uncore frequencies to reach the specified power limit. While there are two time windows, but it's probably not so important for us to measure energy consumption, because with each of these power domains, there is associated register where you can read the accumulated power sample, so the energy consumption, which should it has 32 bits, so which is enough. It obviously depends on how much your CPU consumes, but let's say 150 watts TDP, so some less than 3 minutes may fit into this register before it overflows. AMD is using a similar interface or same interface as Intel RAPL. However, in this case, it's only designed for measuring energy consumption. AMD has a different interface for power capping, and also the power capping interface has its own energy measurement or power monitoring. So in this case, we have two power domains. It's package and core. You can also see that the addresses and names are a little bit different, but the interface, how it looks to the registers and the sysfs interface is similar to Intel ones. So in this case, the most important information is the package consists that the core is inside the package. So while in the case of Intel, when having the package and DRAM power domains, while the platform is not very common to be available. So when evaluating the overall energy consumption, you should make a sum of package and DRAM, while in case of the AMD, you should just monitor the package because the core is already included in the package one. While in this case, it's interesting that you can really monitor each core separately. So you can see the differences in the cores and which core is really loaded. So it provides some additional information in compared to Intel. Another CPU I have in my presentation is Fujitsu A64FX, which is the CPU we know from the Fugaku system that used to be #1 in the top 500. I have this system here because there is one specific feature, and it is a sampling frequency. Each power domain which is provided, which is core, memory, and L2 cache. The power sampling is at the same frequency as each domain, as each piece of hardware. So if the core is under load, it is usually running, they have 4 SKUs. So let's say 2 gigahertz frequency. So the power sampling is really running at 2 gigahertz. However, if the core is idle, there is no power consumption reported. So for idle CPUs, the energy consumption is very far from the reality, because really it consumes some energy, but no energy is reported. So I have here a blade of various components: CPU, GPU, interconnect. So in this case, that's the Oak Ridge, the Frontier system, #1 in the 500 right now. So we have here the AMD CPUs, which we can read from AMD RAPL. So we can have really the energy consumed by the CPU. We can get also energy consumed by the GPUs, which is available from the ROCm, so kind of similar to NVIDIA NVML library or SCMI utility. However, we do not have power monitoring for the remaining components from performance counters, and there is no additional power monitoring solution such as HDM that would give us the overall power consumption. So we are missing some information. We are do not having the information about overall energy consumption. So for that, it's possible to use IPMIs or the redfish, which is follow up, let's say, or a new interface that overcome the IPMI, or yeah, and it provides the power consumption of the whole blade. The problem is that it is running on very, very low frequency, typically one power sample per second, if I'm right. No. One sample per 10 seconds, which is, I think, the maximum frequency that is possible to get out of there. And it again may be different in various platforms, but the power monitoring has way lower frequency in compared to on-node power monitoring and other solutions. So for that, we may, I'm not sure whether you can see the equation I have here again in the slide below the example. I don't know where you can, someone give me a feedback.
Yes, we can see that.
You can see it. Okay, I cannot. Fine. So we should take advantage from the information we have from the high frequency sampling and compose it together with the low frequency sampling information. So measure, let's say, what we can at the higher frequency. So ripple from the CPU, energy consumed from the performance counters, as well as GPUs, while we propose to evaluate typical power consumption of the blade, and which is not covered by the power monitoring we have for the on-node components. So this is called power baseline, and I have here a table for accelerated and non-accelerated partition, where at the top we have Carolina. We have here a Carolina system where we have 8 GPUs on a single node, and we may evaluate the typical power consumption of each GPU and each CPU when there is no load, and slowly, let's say slowly, increase the workload on each piece of hardware. So from that, we have evaluated that there are missing 520 watts when the blade is idle, and if we increase the load on the blade, there it can rise up to 620 watts. So when executing your application, you should add additional watts according the load you put on your hardware. In a very short, I would like to present a runtime system called Merrick, developed at IT4I, which is designed for measurement of the energy consumed by an application, and also for hardware parameters tuning according the application needs. But in our case, we may use this application library to provide you energy measurement of your application. So really, to link your application with the library and instrument to provide you energy consumption of a specific part of the application, or there's also utility which gives you the energy consumption for your application without modifying that. So as it's in an example, measuring energy consumed during 2 seconds of idle hardware on this is some Intel CPU, 2 CPUs actually, package 0 and 1. So it gives you the information, the directly from the various power domains, and also the overall energy consumption. So it knows whether these power domains supposed to be you should have the which are inside each other or not, and also it may not may, but it handles the overflows, for example, for the RAPL. So you do not have to care about that since it samples in time. So the last slide, the information I would like you to take from this part of the webinar, that various power monitoring systems may have various power domains, and these may overlap. So you cannot take all the power domains and make just a sum of all the energy reported per each, because there may be too much, and also you should not pick just a single one, because there are usually several power domains on a single piece of hardware. Performance counters are usually not in joules, but in a fraction of joule, because it is unsigned long, unsigned long, what depends really. But if it would be accumulated in joules, the joule is too large unit. So the precision would be low if it would be in joules. So it's important to understand in what unit the performance counters present the information. So that's kind of a problem, let's say. When you read just directly the performance counters, you really must understand what information it provides you. And that's why I have it in bold and underline. Always read the description of the power monitoring system, what information it reports. You may avoid that if using a tool really designed for the energy consumption measurement, such as Merrick, that has a support for various power monitoring systems. I had it on the previous slide, but from Intel, AMD, NVIDIA, IBM, A64FX, some more. And the last bullet, add also the power baseline, the additional power which is not consumed by the on-node components, to evaluate or server or energy, not server, but blade or node energy consumption, to make a comparable energy measurements from one to another hardware platform. And that's all from my side.
Thank you very